Okay, very good. Can you guys hear me okay? Somebody give me a high sign. Awesome, thank you. Killer. Okay. Okay, I know I always say this, but I think today will be a shorter lecture. Just kind of wrapping up some loose ends on threads. I don't want to go in too deep. It's a very cool subject, but it kind of branches out quickly, and I might be able to squeak some stuff back in, but I mostly want to get you ready for your next and last official assignment. So we'll cover that stuff today, and we'll go over homework 9, and we'll come back to it like with the other ones as well to just try to help people out. But let's take a look at what we have on deck for today, or first look at the outlook of the week. So we're right here at week 15. Homework, or quiz 6 was put up today. I also put up homework 9 a little bit early for those of you that might want to jump into that. A little heads up, no points off for anybody but who may have already started it, but I made some changes to make homework 9 a little less confusing, and we'll talk about those. But otherwise, that's up now and ready to go. And then next week, the quiz and homework 8 will be due. You'll still have lots of time in homework 9. And then we'll just start filling in with some stuff that we can fit in, exceptions and regex. And we'll look at software patterns in our final week and do a little bit of review for the exam. So let me see if we've got everybody. Nobody in the waiting room, good. Oh, right, let me just change one thing here to allow me to hear when anybody joins. Sometimes I miss that, and I would just like to make sure that I hear people when they come into the waiting room. Okay, got it. Okay, so so for today, just want to go over quiz 6 real quick, or just kind of point out that it's there, and then we'll review the high-level stuff from threads last time, and then we will. I want to look at the kind of lab exercise that I put out there on Thursday and just work through a solution for that as a practice, just to warm up. I think it's a good one to do. And then we'll talk about homework 9, and then we'll look at detaching threads, multiple locks, and some ordering issues with multiple locks. And we'll try to look at this thread conditions, see how it goes. I don't want to go too deep in that because we're not going to test on it, but it is an interesting thing to just know about. So with that, any questions before we start out? Okay, cool. Hopefully everybody's taking a look at their homework 8. That's, of course, due next week, but if you can get that in early, that'll all be helpful to you for sure. All right, so our last quiz is going to be quiz 6, and that's got about 14 questions. They're out there now. Those will, of course, all be on the final exam. There's the link for that. Covers destructors, inheritance, the virtual binding topic that we talked about, which I know sort of seemed like it came and went pretty quick, but it's one that I would like you to know. And then it's everything else is the usual. It's the usual 3 tries. And I do encourage everybody to try to do this 3 times. If you don't, it's not the worst thing. You can come back and use it to practice for your final exam, but I will have to take whatever your highest grade was at the deadline. So if I have to reset grades on that, please don't be too surprised. But so far, it seems like everybody's been okay with that and understands the rules. Okay, so let's go just review quickly some of the stuff we saw on Thursday. We looked at the chrono library and the thread library, and we learned a few things. You don't have to memorize these, but one really useful one is being able to put a particular thread to sleep. This kind of helps us debug things, and we could do that in main if we wanted to, which is just a generic and useful way to put any C++ program to sleep. It's the most reliable and cross-platform way in modern C++ to kind of do a pause of execution, but we can do it inside of a thread, which is great. And we can also do it with a variety of different units. So we looked at milliseconds and seconds from the chrono library. So that's how we do that. And if you ever have to do that, we'll give you that code so you can remember how to do it. But if you ever want to dig back on chrono, it's a great library for doing all sorts of timing and stuff. Okay, so So this was kind of the model we talked about. If you think about main being a single thread, we can spawn threads or launch threads from main, and we do that by creating an instance of the thread class. So we feed the thread constructor some information, and it creates a thread instance, and that essentially starts our thread. And we said also that CN was, in terms of pausing a thread, was one example of a routine that we use all the time. We may not have thought about it that way, but it's actually pausing the main thread. And the thing for us that's critical is rejoining threads. And the method is called join. So we take the name of the instance of the thread and we join it back. And we essentially wait there until the thread finishes. So the main thread is going to pause, just like we've seen it do on CN. It's going to pause when we join, waiting for the return of the function, the worker function that we started in our individual threads when we launched them. So we may not even realize that main is pausing here because we may be seeing output or work getting done by our individual threads, but our main thread is really going to be waiting there at the join location. And if it didn't, it would try to finish. And if there were threads sort of still executing, we'd get a crash at the end of the program. So if we get a clean finish with no crashes and it doesn't hang, usually printing a message at the very end of main lets you confirm that you've actually cleaned up everything nicely. Then we know we did everything right with our threads, right? So that was kind of the model we looked at. And remind you that the thread is in fact just an instance of the class and has a number of methods, but essentially when we create an instance of a thread, we give it a name like always, and we pass in the name of the function, not the function with the parentheses. So I'll keep reminding you of this because it will be on quizzes and it'll be on the final, just so you can remember that. We're passing in the function name, which we saw earlier in the semester as something that we could do, is pass in function names to utility functions that we wanted to call. And then the interesting thing about the way threads work is we pass in the arguments to that worker function afterwards. So if do work needs 4 arguments, we're going to have 4 more arguments following the do work name. Okay. So that's the class name, the variable name, if you will, the name of the instance, and then our arguments for the thread constructor, right? That's to construct the thread. And the thread is going to launch the thread, right? So the thread construction is actually going to launch the thread, and your do work function is going to get called. And that's really the lifespan of that particular thread, is just that one function. And it, of course, can call other functions if it knew how to do so, but that's our function primarily. Or that's how we do that launch that worker function. Okay, so, and then we looked at a mutex because we saw that there were problems when we have multiple threads trying to access the same data. So we looked at it in terms of sales, but you can imagine with a database function where maybe multiple threads are trying to grab at and read and write stuff to the database. And I always use the cloud-based scenario. I know it's not C++, but it's a great relevant scenario. If you imagine, many of you trying to access the same Google spreadsheet at the same time, we don't want to have people hammering each other's data, especially while things are being written. So there's got to be some sort of locking scheme on the database that says, hold on, somebody's reading from it or somebody's writing to it. And mutex is one way to do that. Basically, the model, or one model we looked at, was locking the mutex, right? Which means, hey, if it's available, I'll take it and I'll run with it. But if it's not, I'll pause right at the mutex lock and wait for it to become available. That's how these mutexes work. They pause your thread until the lock becomes available. And then when you're done, it's critical that you unlock that mutex, right? If you don't unlock that mutex, the thread never is opened back up, and you get thread lock and your program never finishes. So it's really important, we said, to unlock the mutex. And when you have a lot of if then else's in your worker function, it can be easy to return or quit or leave early without unlocking. And so that was a bit problematic. And so one solution to that we looked at was this idea of a lock guard, right? A lock guard is this RAII concept. It basically says, oh, well, as soon as the lock guard goes out of scope, it should automatically unlock the mutex. It should clean up, which is really kind of the similar concept we saw with shared pointers, if you think of that. So our lock guard, we give it the mutex type as the template. We create the variable name of the lock guard, and we pass it in a pre-existing mutex we've already created somewhere else that we want to be wrapped by this lock guard, okay? So it's a scope-bound lock on the mutex. We can do whatever we want at that point. If we secure the lock, we'll continue and we can do work. And then once we leave scope, whether we return from the function or we leave some inner scope, then that lock card goes away, cleans itself up, and actually unlocks that mutex. So that's just another way to use kind of this RAI concept to ensure we don't create a bunch of thread lock situations. Both ways are totally valid, but this is just the different way, different style of doing it, okay? Any questions on that review material before I go on with our little lab exercise? Okay, cool. Well, let's talk about this idea. And there are more than one ways to do this. I don't know if anybody really took the time to look at it, but I really wanted to walk through this because I do think it's instructional. And I was guessing maybe half of you didn't look at it, maybe more. But let's take a look. So the idea was to develop a simple multi-threaded guessing game where there are two guesser threads that are going to compete to guess a secret number. And that secret number would be, guessed or picked by the main thread and given to, let's say, the individual threads, and they have to play fair. They have to just randomly pick numbers and compare it against the secret number that main passes in. Now, some of you might have tried to approach this from the standpoint of returning a value from the thread. That's a little more complicated, and we haven't covered all that yet, but essentially what I'm going to do here is pass the secret value into the worker thread, as you'll see, so that the worker thread can compare it to a random guess of its own and see if it won or not, right? So the guesser threads are going to keep guessing randomly and keep comparing to the secret number to see if they win. And the worker function that guesses the correct number first is going to try to basically grab the golden ring. It's going to try to set the winning ID to itself. Say, oh, I won the game, or I picked the number first, right? And then the other guesser threads have to actually quit the game if they realize that some other thread wins, right? So we're going to need to be locking a mutex, checking to see who the winner is, or if there's no winner at every iteration inside of these worker functions, okay? And so if you rejoin your threads correctly and you follow the mutex, if you do all that correctly, you'd get a nice clean finish with maybe a message printed at the end and no crash, right? So that's what we want to do. It's maybe sounds complicated. It's not really too bad. We saw a lot of this stuff in some of the exercises we did before. So let's take a look at output from my program, and we'll give you guys a chance to work through a practice on this. I've kind of set stuff up for you, and then we'll go over the code because I think it's good. But so main would say, okay, I'm thinking of a secret number and it happens to be 3, here we go. And launch the threads and tell the threads, okay, the secret number is 3. So thread 3, in my program here, got 3 shots on goal right out of the gate. It got to loop around and try 3 times. Each time it unlocked the mutex, it got to guess again. It just random. It got to be the first one in line between the other 2 threads that were out there. And it was wrong every time until it got to the 3rd or the 4th iteration here, and it actually ended up picking 3, and which was the winner, right? And so the other 2 we want to give up. Like if the other 2 keep trying, then we're in thread lock. So the other 2 have to keep checking to see if a win condition happened, and if they did, then they would quit. Now, this might seem really obscure, but it is sort of relevant to your homework 9, right? There will be a situation in which you're going to be developing a couple separate worker threads that are going to be checking on the health of an avatar in a game, right? So this is a classic game situation we're going to be seeing in a minute about somebody being, a monster attacking an avatar and the health rate going up or down. And so we have to keep checking the health in that case to see if the game's over or not. Here we have a simple winner integer that indicates whether some particular thread has won or not. So it's a little bit different, but a lot of the same concepts. So let's take a look at main. So this is just kind of your hints to kind of get you off and started. And then we'll have you click into the exercise. So main's going to pick a secret number. In my case, I set the secret number from 0 to 9. And so you could have your worker functions do that as well. And I set the ID on the winner to be -1. So I'm going to have threads numbered from 1, 2, 3, 4. And if it turns out that the winner ID is anything other than -1, then we will assume that somebody, one of the threads set that winner value appropriately and win the game. And then there's, of course, our mutex that we use to lock. So main's going to say, I'm thinking of a number, and then we're going to launch these threads and call the do guess method. Now I'm going to pause right there and just give you that much and suggest that, now I don't know if everybody could see the file. Let me just post it again for those of you who joined just a little bit later, because I don't think it actually came up. Okay, bear with me 1 second. Threads, link, there we go. Okay, so so if you would take a look just at what should be I think it's the first link basically in there is what you want to click on. So it should be threaded guessing game practice. That should be the name of the thread. Does everybody see that thread okay in the text file? Give me a thumbs up if you see it okay. Okay, I think I saw a yes out there. Okay. All right, thank you. All right, so take a look at that anyway. I mean, give it a try. Obviously, I want you to kind of give it a try. I'm going to give it a couple minutes, but take a look at that thread and see how the layout is, and see if you can, launch the threads in main. Remember that you want to launch those three threads. In this case, you could have as many as you want. We want to give each of those threads an ID, right? So we need to pass in the worker function itself. That's going to be the do guess function. And then we have to pass in separately the arguments to those. So give that a second, look at it, give it a try in main, and then I'll kind of roll forward to the hint and see if you were on the right path, okay? So I'll just kind of give you a minute or two here before we do that. And ask me any questions if this is confusing. I realize it's kind of a lot of stuff to throw in one exercise. And I'm just going to click into the link.
Yeah, Professor, I have a question. So what this is basically, it's just the two threads failing, passing the guess power to the other thread, through the mutex.
Yes.
And
right.
just doing that until one person gets it.
Exactly. And so if you think about, and I'm trying to remember, let me click in on you won't see this here, but let me click into the practice replit here and remember exactly what I gave you in the code. Bear with me while this comes up. Right. So if you look at do guess, the do guess function, I've kind of left it skeletal for you here. I left in the sleep there. What we'd like you to do, you can leave the sleep at 0 seconds. You can set it to 1. But basically, the first thing you want to do inside of that while true loop is grab the lock if you can. So you're going to try to secure the mutex, right? And remember that M right there is a pointer. So that M star M is a mutex pointer. And so inside of there, you're going to try to grab that lock, and then you're going to, guess and compare to the secret number, right? Mm-hmm. Now, if you want to just start out though, in main and just try to lay out main first, pretend that your do work function or do guess function is working. We'll come to that in kind of a second hint kind of thing. So maybe try main first, and then we'll come back and give you a hint on do guess. Okay. So I'll give you another minute or so on that, since I sort of just talked over all that time. So I realize you probably don't have all the syntax memorized, and it's understandable if you had to kind of look back at the PowerPoints or something, but um, it's relatively straightforward. If you remember, you have an instance name of a thread, and then you can join the thread. So if you kind of remember a few keywords, it makes things a little bit easier. But let's take a look at mainnet now and see how that plays out. So we have our mutex, which exists, in the scope of main, right? It's a variable in main, and then we have winner, which is also an integer variable in main. Right? And so we're going to pick a number. We picked a number up above, right? So I guess this is not much of a hint, is it? I thought this was a little more of a hint than I put here. I think we'll come back and add some stuff to it. But basically, you're just going to create 3 instances of thread, T1, T2, and T3, right? And the arguments to that constructor is going to be the doGuess function name without the parentheses, right? So you can think of that as being the first input to the function is just the name of the input to the constructor for thread T1 and T2 and T3 is the name of doGuess. And then followed by the doGuess arguments, which if we look at the doGuess function, you can see we want to send in the secret number. We want to send in the address of the mutex so that we can change the mutex. Now, remember that we could also pass this in by reference, but because the doGuess function has its function signature expecting a pointer to a mutex, we have to pass in the address of M, right? And then an integer ID just to help the thread know who it is, so it can kind of write stuff out. So we just pass in 1, 2, or 3, whatever ID we want to give to the thread. And then, the input output, in other words, the pointer to winner, so that if the thread wins, it can declare itself a winner. It can set the winner value to be its particular ID, right? And then we have to rejoin, which is just the name of the thread, sort of rejoining or using the join function for each thread, right? So let's take a look at doGuess. So here's a hint. We'll kind of lay this out and then see if anybody wants to take a minute and kind of finish this one. But the idea here is, so we have while true. We want to get the lock, right? Remember that M, as I mentioned before, M is a pointer. So it's really going to be something along the lines of M arrow call method for locking, which you could probably guess what that method is called. And then if you get the lock, if you don't get the lock, you'll wait there, right? Of course. If you do get the lock, then it's your turn to check and see if the game is over. Now, this is really relevant for your homework, because if you jump into a thread for one of your kind of either your health thread or your monster thread, as we'll see, and the game's already over, but you start going to work, you may end up in a thread lock situation. So it's important to figure out if the game's over right away. So if we check star winner and it's still -1, then we know we have no winner yet, right? Otherwise, if some other thread has won, we can print a message, unlock our mutex, and return, right? So it's possible that we actually might have acquired the mutex after the game was essentially over, right? Before main exits. So it's important for us to check this condition. Otherwise, we could create thread lock. And some of you will end up doing this. It's an understandable mistake, but it's important to check that right away. Otherwise, right, if nobody won, then we'll try one guess from 0 to 9, right? And then you can print that out for debug purposes, and then check it and compare it against the secret number. And if it matches, then we are the winner. So we can set the winner ID equal to be my ID, right, which is the ID of this particular thread. It's passed in as a function call. Print a message and definitely unlock the mutex, right, and then return. Now, if we used a lock guard, we wouldn't have to explicitly unlock the mutex because the lock guard would go out of scope. But we wrote this one, I wrote this one anyway, just using the unlock for the mutex. Now, if we get a wrong guess, we can do something else. We could print a little taunt message or whatever, and then go ahead and unlock the mutex as well, and then do a sleep, right? So sleep for 1 second, right? And essentially what we're doing is we're giving the other threads a chance to guess while we're sleeping for 1 second, if we sleep for 1 second. If we don't sleep for 1 second, if we sleep for 0 seconds here, we're going to pop right back around in the while loop and take a shot at grabbing the mutex again. And as you saw from my output thread 3, I think if you recall, kind of got 3 shots at guessing and ultimately won the guess, right? So if we sleep before the lock, it does no good, right? If we put that sleep before we unlock the mutex, so in other words, if we move this line above the unlock of the mutex, it really does no good. It just puts us to sleep, but everybody else is waiting on our mutex anyway. So it's really not giving the other threads a chance to grab the mutex. So in this particular model, you know, to be quote unquote fair, we put this sleep after we unlock the mutex, right? Now, if you don't sleep for anything more than 0, it makes no difference, but we can change that, right? So now let's take a look at the code solutions for those of you who tried this. So here's how we did it in this case. So we create these 3 threads, right? Pass in the worker function, pass in the secret number, which is just for comparison purposes. Pass in the address of the mutex, the thread ID, and the address of the winner variable so that each thread can change that variable. And of course, it's not going to change that variable as we just saw unless the mutex is available to that specific thread. And then we join those threads back up, and a little closing message just so we know that the execution finished normally. Okay.
Professor, I have a question.
Yeah. Yeah.
Why?
Whoops. Did I lose you?
Oh, sorry. 1 sec. Why are we calling the reference to winner, like passing it in here, instead of writing the function to ask for the reference of winner?
Instead of asking the function.
You know what I mean? So the function is asking for a pointer to the winner variable,
Yes.
the winner integer.
Yes.
Wouldn't it be simpler? I know it's probably a style thing, but wouldn't it be simpler just to like have the function ask for a reference to winner and then just pass it the winner, you know, without
instead of passing in the address? Sure. Yeah. So in other words, if do guess function signature had a reference to winner, it's the same difference, right? Yeah, we could just
doesn't really matter.
Yeah, exactly. It's a style thing, and you know, you could say there's maybe some efficiency gains there depending on what kind of data that we're passing through here. But yeah, otherwise it's the same. It's really a pass by reference solution here is what we're really doing. So there's our main, and so yeah, and so here's exactly so that, and I actually was thinking of rewriting this, but a little hint there might be a quiz question that is based on references rather than addresses. So yeah, this could have been int ampersand winner, and this could have been mutex ampersand m, and it would have accomplished the same thing as long as we called it appropriately in main, right? Which, you know, we wouldn't have to pass in the address at all. So here's our kind of you know, a solution to this. So we lock the mutex, which means we wait there if we don't win and get the lock. Otherwise, we can do as we saw in the pseudocode before. We can just say if the what's at winner is not equal to -1, then somebody else already won the game because we trust that they set it to their winning ID. And so we unlock and return. Otherwise, we'll take a guess, and then we'll print out our guess just for diagnostic purposes, compare it to the secret number. And if we did get the right guess, we set the winning ID and unlock and return, right? And so kind of just follows, you know, pretty much the way the pseudocode was. But the syntax is not too complicated. The key thing here is if this was, and this will be important for, I mean, I hope you guys understand this by now about the difference between references and addresses. If this was a reference, you'd say, or if mutex was a reference, you'd say m dot unlock, right? But since it's an address, we say m arrow unlock. Hopefully that's starting to gel for you guys. But otherwise, the syntax is pretty straightforward. We're just unlocking a mutex or setting some variable through reference, right? And then we return. Okay. So that's a way to do that. There are other ways. I'm not sure if we'll get into promises, which is, somebody had a great question the other day about how do we return values from these worker functions, because as you can see, it's void. And if we go back and you look at how we call these functions in main, You can see there's no real way here to get a value back from do guess. So a number of languages have a concept called promises, which is another RAII approach to creating this kind of safe place to store a return. It's really an instance of something. So it's an instance of a promise. It's kind of off in an area of memory where usually where we create the threads, where we actually allow this thing to pass a value back. And you can wait on the promise to be returned. A promise means, hey, I'll get you something, just wait right here. And promises are used very, very often, especially in database programming in the web, because they allow you to write code as if your flow is going to continue, but you're basically saying, hey, I'm going to wait on this thread right here until it gives me the answer. So let's say T1 here was computing some really, really complex problem that took a lot of time, or it had to go get something from a database. When you go get something from a database, that usually takes a whole lot longer than it takes to execute a line of code. So that means you got to wait on that thread to return what you wanted. And so promises are a way to get values back from a worker function. So we're not doing that here, but it's something I hope to actually show you guys, but I'm not sure if we'll have the time. I know we won't go through it today, but just wanted to throw it out there because I know somebody asked about that. So anyway, that's our kind of lab sample work through. So what I want to do next, unless there are any other questions on this the lab suggestion from last lecture, everybody cool with that? Okay. Okay, so let's talk about homework 9. So I like this one. Apologies for the delay. This was actually split across 3 homeworks last year, and it was just that we just couldn't fit it all in. So I really was trying hard to consolidate this down into 1 or 2. So this particular homework, we're going to create a maze. We're going to have a monster or a boss in it. I called it a boss in the code, but it's just a monster. And then you, the avatar. So you're just going to be running around this open maze trying to escape this boss creature. It's not quite a game per se. It's really just an exercise of seeing whether all your threads are working correctly. And we'll have 2 different threads executing and doing different things, and we'll go through that. But the idea is that you have the main thread, which is you kind of moving your avatar around, and you should be able to do that with things that you know already, right? We're just drawing a grid, we're putting stars around the outside of it. We don't want the avatar to ever be able to leave the grid, but we want to move left, right, up, and down. And we'll do that by typing a character on the keyboard and hitting enter. We've done that kinds of things a number of times. So that's one part of the assignment, right? But separately, we want to have this worker thread, we'll call it the boss thread, that's going to constantly try to move toward the avatar 1 square per cycle. So the boss thread takes a 1 second sleep every time it loops in that infinite loop, then that's going to be 1 square of movement. And meanwhile, we want you, the player, to be able to run away from the boss. And so the main thread is you kind of entering directions in as quickly as you can, and then it's constantly chasing after you. And then if it attacks you, in other words, when it's coincident with you, it's going to decrement your health. So the boss thread is going to try to grab a mutex, lock it, and decrement your health, because that's the common thing here that needs to be protected is your current avatar health, right? So it's going to, if it gets the mutex, it's going to decrement the health. It's going to sleep and then just repeat. Meanwhile, we want your avatar to constantly be regaining health, right? The longer you stay alive, the more chance you have to recover your health. So you run away after an attack, and then the health thread is going to allow you to gradually get your health back. And so that's a really simple thread too. It's just going to sleep and then add some health back, sleep and add some health back, as long as the game is not over, right? So for both of these threads, and this is to that point I made just previously, you really don't want to try to do stuff if the game is over. So you will have to check and see whether the game is over. And we'll see a few member variables that would help you manage that. So but those are your 2 main threads in addition to main, right? And so that's kind of the gist of the game. I think I'm going to try to just run a sample of this real quick. Bear with me while I kind of launch it and get it configured so you can watch it, because we've not done anything quite like this. It's a little bit wonky. I mean, Replit is not ideal for this, but I think we can do it. I'm not going to obviously share the solution code with you, but this is from my solution set. So let me get things rigged here before I start it. Now I'm going to swap the share over to a different screen. Let me see if I can do that. New share. Okay, there it is. So my new share is going to be, boy, which one is which? Aha. Yeah, that's the one. Okay. So let me share that and see. Does everybody see my Replit window now? Or somebody give me a thumbs up if you see it. Hopefully it's there. Cool. All right. Thank you. All right. So let me just run this thing and get a few things out of the way so you can kind of see what it should look like when it runs. So you're going to notice that it's going to just keep updating the screen. So it's just redrawing the whole screen, right? So I'm going to type, I'm going to type A to go left, right? And W to go up. Are you guys familiar with WASD controls for old school gaming? So we've got a keyboard, maybe everybody knows this, but WASD are kind of up, down, left, right directions. And this is all described in the code. But basically, I'm just, every time I move, the grid is getting reprinted. But also, every time the boss moves, it's reprinting the grid too, because it knows that it moved and it wants to update the grid. So there's a whole lot of printing going on by multiple threads. And my health is constantly being refreshed up to a level of 100. So you can see my current health there at the bottom. Now I'm going to let it kind of come over and attack me. And you should see my health start going down because it's kind of hitting me. And this has a bonus feature in it, which is I stayed alive long enough to win the game. We'll talk about that in the bonus part. But basically, let me rerun it again and I'll just let it kill me so you can kind of see what's going on. So I won't even move, right? So you'll see it coming over and my health is going down, it's going down, it's going down. And essentially, if my health gets to 0, it's not able to recover fast enough, then the game should be over. So you have these competing threads, basically trying to modify the health, and that's they all have to use the thread lock in a reasonable way. Okay, so before I leave this window, are there any questions that would benefit from me staying on this window? Okay, cool. Not a big deal. Let me just move back over to PowerPoint then. Okay, get all these things out of my screen. Okay, so that's kind of what we're after here. So it's not too much code really, but the tricky part, of course, is just getting familiar with the classes. So let me go through a few members of the classes and things that you might want to know. So the WASD keys is how we're going to kind of do this one-handed input for navigation. So you're going to type a key and then you're going to hit enter, and that's unfortunately we're stuck with that for input for Replit. And we're going to predefine via the const members of the maze class what up, down, left, and right means. And we're going to refer to those via the up, down, left, and right members. So I hope in your code you are not testing for W, S, A, or D. I hope you're testing against up, down, left, or right, because you'll lose a couple minor points on that one. So we're really just trying to have some abstraction so we can change those values if we want, right? Key thing there is just that they're const values, so we can kind of lock them and initialize them. So now here's a couple other members that are important for you to understand. So we want our constructor to be able to modify what the grid looks like, right? So an empty token is the token in the middle of the maze where there's nothing, right? So it could be a blank or it could be a dash. We want the constructor for the maze to be able to specify that. And also we want the constructor to be able to specify the wall token, right? So these are members that they're just care members of the maze that you'll need to set. And then for the purposes of, various things in your loops, mostly in take turn and boss move, you want to know the dimension of the maze. Now you could get this from looking at the grid and finding out one of its dimensions, but since it's part of the constructor, it's useful to just kind of save it in a member. And then you're going to use that dimension to create a square grid that's dim by dim, a vector of characters that represent the entire maze. Now, I'll say this multiple times, but you don't want to store the character for the avatar or the boss, that is the monster, in the grid member, okay? We just want to store the maze in the grid. And then we will, when we print the grid, we will overlay the avatar's position and the monster's position. But you don't want to store them in the grid. Every year somebody does this. I understand why, but I'm just saying this, and we'll say it a few more times to save you the headaches, because you get so confused of why your avatar isn't moving, right? So don't, or you got multiple avatars in the grid. So don't do that. Then our avatar token is just as you might expect. It's the letter A or whatever you want it to be. And then the location, these are members of the maze class, the location of the current avatar and its health, right? So these are members associated with the avatar, and the health mutex. So this is how we lock and manage access to that health mutex across multiple threads. And then we have our health thread. So this is the instance of the thread class that manages your avatar's health. And there's the worker function associated with that health, okay? And then we have a boss token or the monster token. And then we have its location and its thread, okay? So those are pretty much the key members. Is there another one? Oh yeah, no, sorry, the worker function for the boss, right? So this is the thing that you're gonna write as well to move that thing around. Remember, we don't need a thread for moving the avatar because that's main. So main is invoking that. It's, even though it's calling the take turn method for maze like we've done before, it's happening in the main thread, if you will, or the thread 0 if we want to number them, right? So those are kind of the key components of the whole game. Anybody have any questions on that? We'll see more pictures of this and elaborate, but just want to see if.
So, oh yeah, I have a question. So when it attacks, let's see here, it attacks when it's on it.
Yes, when they're coincident, whether you move on to the boss or the boss moves on to you. If they're coincident at a point, the boss thread will do damage to you. So when the boss thread is looping each cycle, it's going to go, oh, I'm on top of the avatar, subtract some points, subtract some health points. Yeah, but only when it gets the mutex, right? So it has to be able to acquire the mutex.
Yeah, and it the boss moves what, every second, or it tries to move every second?
Yeah, I think we set it at every second, but it might be part of the boss constructor. So there's one part of the assignment where it says, have fun tuning the delays on all of these things, to make the game fun or playable anyway. So yeah, I think basically the arguments for the boss, the move boss thread, the worker thread for the boss allows you to tune that a little bit. Same for the update health. I think you can modify the update health function by sending in some different arguments that you'll see once you read the canvas thing there. Okay. And then the game over, that's the key thing. That's kind of like that winner variable we talked about in that last exercise. So game over, we want you to check right away, really, when you enter the boss thread or when you loop around the boss thread. Because every time you reacquire the mutex inside of the boss thread, it's a whole new ball game, right? So if you check game over just at the beginning of the function before you acquire the mutex, it's not going to do you any good. You really need to, after you acquire the mutex inside of these threads, check the game over flag to decide whether you got to leave or not. And then you unlock the mutex and leave, right? So where most people get into trouble, or just it's a process, you get thread lock, you're trying to figure out why, and you got to go back in and look at your worker functions and figure out what you forgot to unlock and where. Okay. So, and here's the one of many reminders. So it's understandable you think you need to store the avatar in the grid and you need to store the boss in the grid, But the reason we don't do that is because then every time you move the boss or the avatar, you got to go erase where the avatar was and erase where the boss was and draw them in their new location. And so what we do is we just, in the print grid function, that's where we actually decide to overdraw the grid with at that specific location with the avatar or boss, depending on where their location is. Okay. So those are kind of the key maze data members. Any other questions on that before I move on? Okay, just a couple more slides on this. So things that kind of have already been done for you. So I wrote the print instructions to just try to, reinforce this idea of move up, left, right, down. It's really about checking the left, right, up, or down members of the function, not the characters, WASD. And then I wrote main, so it just creates the instance of your constructor, right? And it's going to call print grid, every time, well, in the beginning, and then it's just going to keep looping until the game is over, right? The game is only going to be over when your health runs out. So in main, we just keep checking to see whether game is over. And if it is, if some thread sets it to be over, either the boss thread, because you're out of health, or the update health thread rather, because you're out of health, then the game will be over. Otherwise, we take our turn and we print the grid again. Okay. Now, and this is the thing we'll spend one exercise on. So we want to actually launch our threads from the constructor of the maze, and then we want to rejoin those threads in the destructor for the maze. And we'll do an exercise on this just to help reinforce this. But this is a new idea, actually letting our existence of our maze class be the place rather than main that actually creates our threads. Because as you can imagine, this gives us an opportunity to create lots and lots of threads that we create and then rejoin in the destructor, which is a really cool way to do it. Okay, so we'll go through that, right? If you don't rejoin your threads, as some of you remember from Thursday, you'll crash. And so if you forget to do this part of the assignment, you will definitely crash, because your maze instance will go away at the end of main, and those threads will still be hanging there unjoined, right? So that's something that we'll have to do. Okay. Any questions on just the main part there?
Yeah.
Yes.
When is take turn called? In a loop, right?
Yeah, so this is kind of a model we followed before, and some people, in their own, I forget which assignment it was, some people kind of integrated the whole take turn thing into the class itself. The way I've done this class for you is you just call the maze take turn and give it the direction that just got entered, the string basically that just got entered at the keyboard by you. So if you type W enter, that's a string, and that gets fed to the take turn method. And it will say, oh, you want to move the avatar left or right or up or down. And it's got to check for a wall, make sure it's not going through a wall.
Yeah.
Like that. Yeah. The other, which we didn't do with this, I thought it might have been too much, was, we did, last year, we did a smaller version of this that had walls everywhere. And so you kind of had to move your boss around the walls and avoid the walls, and your avatar needed to avoid the walls, and that with threads just looked like it was too much for me to give you guys all at once. So yeah.
And so this CN is running parallel to the threads.
Exactly. So it is by all rights in its own thread. And to be really correct, main should try to acquire the lock before checking game over. But because main is not setting game over, we're just reading it, we're probably okay to do that, but it is a little sloppy. But I've written this for you, and so hopefully it gives you kind of a model on how this is going to work. Okay, so let's look at how we launch the thread from the constructor. So we can do it this way. This is normally how we learned how to do it, right? We said we pass in the name of the function, and then whatever arguments, and I've just created a fictional function here. This is not from the homework, but we just pass in whatever arguments that do work once after those, no parentheses. And the creation of that thread launches that. Now, that when we're launching from a constructor will only work if the do work method is static, right? If the do work method is static, it's easy for the myThread constructor to basically find it, if you will, and invoke it. If it's not static, remember when it's static, it lives in the class, not in the instance. So if it's static, it's easy for the myThread constructor to find it and call it. But if it wasn't static, if the doWork method lived in the instance, in other words, if it wasn't static, it was just in the instance, we got to go through a lot more syntax, which is interesting, but very, very specific, in order to tell the thread constructor, hey, we want our thread to actually come from this reference of the maze class, which is moveBoss, and then we're going to send in this, which is a special pointer to that instance, and then we can list the arguments for whatever that worker function is, right? So that's so when I first put out the assignment, earlier today, I had not simplified things by converting doWork to be static. So it's okay if you started and you're going down this path right here. You'll need to launch your threads using this syntax here, and I'll help you with that. But if you want to go back and just grab a fresh copy of the link that's in the Canvas document, then you'll be fine. And if you haven't read the Canvas document, you'll be fine, because once you get there, you'll see this link. So apologies to the folks that jumped on early, but I thought it might be more sane for everybody if I could just help you avoid all the syntax, because this is not a very common syntax to use. And one more thing, if you think about it, like if we had 1,000 bosses, do we really need to have a unique copy of the doWork function in every instance of the boss? No, not really. I mean, it's the same function for everybody, so we might as well just make it static and put it in the class itself, and it's more optimum that way. Okay. So that's the little change up since I posted that this morning. And then in our destructor, we need to rejoin the thread. So all the threads that you're doing, the update health thread, the boss thread, if you do the bonus for the playtime thread, you'd have to rejoin that in the destructor. We're going to do it in the destructor. You could do it in the main loop, but we want this thing to be all self-contained, right? So when we destruct the maze class, or we try to and say, okay, I'm done with the game now, I want to delete it, we want it to actually join the threads at that point in time. And we'll see this in our exercise, but it's a little bit interesting how it actually works. But so basically inside of your maze destructor, you would just join those threads in. So pretty straightforward, unless you forget it, and then you'll have a crash. But that's
yeah. And Professor, I got another question.
Yeah, go ahead.
Does this, and also you're joining the threads in the structure in the destructor. That means we're doing that so we can like arbitrarily end the game, right? We don't have to be reliant on the main finishing, right?
Well, go ahead and finish your question.
I mean, if you think about it, like you can get killed by the boss before you see in another letter, for instance.
True. Good observation. And that is one little problem, that the CN might hang if you're dead. You might not know you're dead yet. And this would be one reason to rewrite main to use the mutex lock a little more thoroughly. But it's, as we'll see in this upcoming exercise, it's not true that that main can just quit at any time, because it's going to have to wait for the boss thread and the health thread to finish their jobs. And they should finish their jobs if the game is over. But if you don't finish the game, then they will hang you up. So, and we'll see this in detail on this next exercise. And the reason I did that is because it is a bit of a gotcha. So I just wanted to work everybody through it. So I think that'll help. So yeah, here's some of that. So your threads can finish while your main loop is waiting on CN. So that, I think you were making a point similar to that. And so you may find, and I hope nobody beats themselves up about it. I had some people last year, they were just staying up till midnight, couldn't figure out how to get their code to terminate. And it turned out that they just needed to type left, right, up, down, and hit enter. And then it would normally terminate because it was just hung on that input. It doesn't happen all the time, but it can happen. But otherwise, if you can see your game over message and you see your destructor message, and you don't have some sort of error condition, then you're good, right? So that's all working in concert. It's not a lot of code, really. The most complicated thing might just be, trying not to exit the maze and how to build your grid again. But the thread stuff should be all kind of the same stuff that you guys have seen. So that's homework 9. You got about 3 weeks to do that. That's our last official homework out of 9 homeworks, right? And so you're really just going to be working in maze.cpp. If you made any maze.h changes as required, or if they were necessary for the bonus, you can of course update that, or you can just send in your URL as always, and have fun with moving the boss around. Because it doesn't have to just move one. You could try to be, make it fun. I'm not going to count points off if you move 2, or if you move random, or if you get aggressive because you got close once to the avatar and then you couldn't anymore. That's okay. Have fun with that if you want. And then I still owe you guys a optional homework 10. So I'm really this is for anybody who would want to just try to do that to swap out one of their low grades. So I'm going to try to get you that as soon as I can, probably tomorrow. I apologize for not getting that sooner, but that'll allow people who have the time, once I get this out, to maybe go after one more thing. And originally I was going to make it a follow-on to this exact homework to incorporate the virtual pointer, virtual methods that we talked about in inheritance. So I may still yet do that. So that would require that you successfully complete this particular assignment in order to really understand how to extend from there. But I'll let you know by end of day tomorrow what that's going to be all about. Okay. Any questions on homework 9 before we go on? Okay, cool. All right, so let's just do an exercise here. So a lot of this will be a little bit redundant to the information that we just went over, but I just wanted to have you get hands on it and be able to see it. And I'm gonna, while we're at it, post this one more time. I can't remember if everybody got to see the links, but just in case, I want to make sure that's up there. So bear with me. One more time. There's our, yeah, so those are our links. Okay, so let's look at managing threads within class. We're going to do exactly what we just talked about, right? So we said this is, how we would do it, the same way we would normally do it, as long as our class worker function is static, right? And this is that RAII principle at work. So we're actually designing our class so that when the maze class goes away, it's going to clean up its threads. So that's really what we want to do. So if that doesn't kind of jive with, here's kind of how that lays out. And really, this is what's going on in main in your homework. So we have some class, in this case foo, but in the homework it's maze. So we're going to say foo star f equals new foo. So we're putting an instance of foo on the heap, right? And this is our default constructor. So foo doesn't need any arguments here. But f is now on the heap. It's an instance of foo, right? It doesn't have its worker function stored in the instance. It's actually stored back here in the class because it's static. Okay, that's what we're doing in the homework, and that's what we're going to do in this exercise. But we do have a constructor where we're going to create the foo thread, an instance of a thread, right? And then later on, we're going to rejoin, and I forgot my parentheses, sorry, that thread in our destructor. That's the name of the game here, right? So when we actually call the constructor and we create that thread and we pass it the do work function, that spawns our worker thread that goes to work and does work. Maybe it's the boss or the health thread or whatever. And then when we delete F, and this is really interesting. So we're going to say delete F. And these two lines of code are going to live right after each other in main, right? So we create the instance and we immediately try to delete the instance. Well, that seems kind of crazy, right? Because aren't we playing a game, or doesn't do work have to work? Well, because of the way we're doing this join, delete is going to block on the destructor, right? So the destructor in our class is going to say, oh, well, okay, I'll destruct, but the thread's not back yet. I'm blocking on the thread because it's still doing work. So we'll see in this upcoming exercise that even though we delete F here, we end up blocking at this point because the destructor is also blocking. So F is an instance. It's trying to destruct, but the destructor's saying, oh, got a thread I'm waiting on, hold up. And so we'll move to this point in execution and pause right there, and the whole game could happen in the space between those two lines, right? Because of the way we set up our class. All right, so when the do work is done, then we can finish, and our destructor will finish, and we move on, which could be the end of the game or whatever, maybe some other phase of the game. Okay, so that's the way we're going to set this up for homework 9 too. So let's see if we can do this. Hopefully it's not too much, but it'll at least give you a model you can come back and look at. So so consider the foo class when you look at it. Its constructor takes a sleep seconds argument. So the foo class just is going to pass that on to the worker class when it launches a thread, right? So it's going to pass the sleep seconds into the do work thread when it calls it, right? And here again, as we mentioned, the do work thread in our class, you'll see is going to be static. And if you want to click in and look at this code while I'm talking about it, you certainly can. It'll probably help the conversation. But so the idea is that thing is static, and we're going to create this foo thread as a member of the class that represents that thread instance. And we want to launch that with the do work function and pass it in sleep seconds, right? So it's really going to only have two arguments. The constructor, launch a thread from the foo constructor for creating the foo thread with two arguments, do work and sleep seconds, right? And then in the destructor, you rejoin the thread via the foo thread join method, right? And then in main, go ahead and just create an instance, pass it into integer, and then delete an instance, right? So that's what we want to do. I think that's the last one, right? And then print a done message. So click into that if you would, and I'm going to give you about 3 minutes on that one, and I'll maybe just narrate over the top of the trickier parts as you go and see if I can lead you guys to success on this one, okay? So I'm going to take a look here at it while you guys are working. Let me know if you have any questions. I'll offer one thing. You might notice because we have a member of the class that is thread, right? That foo thread starts out life as a null instance, if you will, of a thread. It doesn't launch anything. The constructor is the default constructor, so nothing happens. And it's up to you to, via the copy constructor essentially is assign a new thread copy to foo thread. So you'll be invoking the thread class directly and giving it some arguments. And I think we saw that example on the previous slide too. So give that a try. Okay, just another couple minutes or seconds here. Okay. So, and one thing, I hope it's a little different model than we've done before. The idea here is the do work thread is just going to do one thing of work for a number of seconds and quit, right? So it's not looping around or anything. It's just going to try to execute, do something to keep itself busy for a little while. So let's take a look at how that stuff lays out, right? Um, so here's our do work function. It's really just going to print some obscure message that says it's working. Oops, sorry, I got that in there twice. And then it's going to go to sleep. And it's going to go to sleep for the number of seconds that it was told to sleep for when the thread was launched. Remember, that launching is done by the thread class itself. It calls do work and feeds it the sleep seconds argument, right? And that's it. That's really all we're doing in this particular case. There's no mutex, no lock that we need because we're not modifying any data in this particular example, right? The important thing to remember here is that in this case, do work is static. And I don't have it listed as static here because this is an out of class kind of specification, which would, the prototype in this case would have a static designation. But in your homework, you'll see, or you'll see this as actually, will need to be, the static is in the .h file already. You don't have to worry about it. When you implement your do work, it'll look similar to this, basically. You won't have to restate the static, right? So, and then in main, right? So here's our foo f. So we can say new foo 5-second delay if we want. We're feeding in the 5-second delay for ultimately for the do work method. And then we say delete, right? And this is where we're going to wait, right? So delete is going to hang, which is kind of strange when you think about it. It's like, why would we block on F here when we try to delete it? Well, it's because that destructor is going to actually, wait for the thread to come back. So we'll look at that, I think, in the next slide. Okay, so there's that. So here's our constructor, right? So really simple, very straightforward, pretty easy format in that case. And then here's our destructor, also very simple, right? Foo thread.join. And then we could print out a message after that join is done that says, hey, we're done now, right? But what you'll notice, if you did print this thing out this way, we'll see this on the next slide, that we right away go straight to our destructor, right? So you'll see this, this destructor message show up right away, but it's really going to block on the worker thread. It's going to sit there for some number of seconds, right? So here's what that output might look like. We created foo instance. We're right away, we just immediately go to joining the thread in the destructor, but that's where we block because do work is working and we see the feedback from do work, and then the destructor can finish, and then the main can finish, right? So there's the kind of the way that all wraps down. So it's a little bit laborious to go through it, but it is kind of illuminating if you haven't totally wrapped your mind around how these things work, that the delays are going to come where the thread gets blocked, and that could kind of emanate outward and ultimately hang your program if you don't resolve these things correctly. Okay. Any questions on that one? Okay, cool. All right, well, we're clicking through this stuff pretty easy. That's kind of our main takeaway for today. I did want to just mention detaching threads. We don't have a lot of examples, unfortunately. We could spend a whole week or two on threads, and it'd be really fun actually to come up with some good exercises. But you can imagine that some threads you just don't really maybe care about. You just want them to kind of go off and do some things until maybe you decide that you want to finish the program. So if we detach the threads, and this might have been what you had in mind, or maybe slightly called into being earlier, Ben, I think, with your question is, it would be nice if you could just leave main, and if there were threads out there that you didn't really care about, they would just finish and not hang you up. And the way we do that is we intentionally detach the threads. We say, okay, well, we actually don't care about how they finish. They're doing something, interesting but not critical, and so we'll just detach them and then let them go, right? And so if we don't detach them, we're going to try to join them at the end to prevent a crash. But if they're detached, they are not rejoinable. We can't really join them anymore.
Yeah.
Question?
What do we do if the main function ends before these detached threads are done? What happens?
So the operating system, it depends on the operating system, but basically the operating system decides whether the application persists or not, so that that thread can do something. I think probably for most operating systems that we work on, Linux or Mac or Windows, basically the operating system is going to shut down any detached threads when the main thread finishes. But there could be situations where it might allow those threads to continue. And the implication is those threads need access to all the memory that went along with the main program. So it prevents that program from really leaving memory. And if you've ever kind of had to deal with, Linux, at a operating system level, and you monitor like, hey, I killed that thing, why won't it go away? If you've ever killed processes even on your Windows or MacBook, it's like, hey, I killed that thing, why won't it go away? Well, those are situations where those applications are allowed to persist their threads even though you've killed the main application, and it may be going through some cleanup process. So you can detach these threads, but I think very often the programs that we run don't have priority such that those threads can prevent it from finishing. I think the operating system will kill it.
That makes sense.
Yeah.
So, what is it? Why attach a thread to main to begin with? I might be blanking out here.
No, it's a good question. I mean, it really depends on what you're trying to accomplish. We've been looking at a very specific kind of world where we want to know that a particular thread finished its job. So take the case of our guessing game, right? Like we don't want to quit the game until one of the threads wins, right? So we need a way to block main, because think of main like a freight train. It's just going to charge forward and finish if we don't do something to stop it, and then the game's over, or the execution of the program is over. So joining is a way to block on a particular thread until it comes back. Now, if we were doing something, I realize I always pick on particles, but let's say every particle flying in the air in some simulation was a thread. That'd be kind of crazy, but we really don't care. It's there for cosmetic purposes. We really don't care, whether they die when the program dies. We just want them to keep doing their thing for as long as, the game is running. But when we run, we want to just kill them all, right? So we could detach those threads and just let them go on their merry way and do whatever it is they're doing. And maybe they're colliding with each other, so they're checking some common data trove of where other particles are, but we don't really need to rejoin them at the end, really. When we decide the game's over, we'll decide the game's over, right? We don't need to depend on those. So it really depends on what you're using the thread for, I think.
I see.
Yeah, okay, cool. And as we'll see here in one of these exercises, if we leave the program, we kind of, at least in Replic's case, we really don't even have a means of actually seeing if those threads are still doing anything. So if we were to try to debug a program like this, we need other ways to sort of monitor those detached threads because they're just kind of off, right? But in certain operating systems, like I said, they could maintain access to global data, which prevents you from freeing up maybe some bloated program that you're trying to kill, right? And it's just taking up all of your RAM, and you can't get rid of it because some thread is still active. Okay? So let's just look at the syntax for that. Excuse me. Very straightforward. So basically, we launch our thread, and then we could detach it, right? So we detach it, it's no longer part. Now, if we try to join that, once it's detached, we're going to get a crash, or because it's going to say, hey, this thread isn't part of you anymore. You can't join it. So there's this sort of if joinable test. We can say if T is joinable. I say is joinable, but the is not in there. But basically, if T.joinable is true, then go ahead and join. That's the safe way to try to join a thread if you don't know whether it's been detached or not, right? And so that's a good idea to use if you're actually writing in a large base of code where you're just not sure how somebody actually went and launched that thread in the first place. Okay, so that would be how we actually do that detach. Okay, so if it's detached and we try to rejoin, you know, we would run into trouble. But otherwise, we'd exit main immediately, right? If it was if joinable returns false, right? If it's not joinable, we're out of there. We're just going to quit. Okay. Okay. So I don't have a really, well, I have maybe an understandable example of this. We'll try this one. It's a little contrived, and let me just check the time. This is probably all that we have time for, but let's give it a try. So basically, we're going to have this continuous two processes: one, a selling behavior, and then a reporting behavior, right? And we're going to detach the selling thread from main and see what happens, right, when we try to rejoin it. And so what we want to do is just incorporate this test for joinable so we don't crash the program. So we're going to say, if it's rejoinable, then go ahead and do it. Otherwise, we'll just kind of continue on, right? But we're going to run the reporting thread until it actually runs out of inventory, right? So, so what we want you to do is create a new thread that calls the report function to report on available inventory, and don't detach the reporting threads. We're going to keep the reporting thread attached to the main, but we're going to detach the selling thread. So selling is off there, just selling inventory as fast as it can possibly go, right? There's nothing we can do to stop it. But report is going to be checking on the inventory, and when the inventory is gone, report is going to come back to main through the join, and that's when we'll exit the program. We're like, well, okay, we're quitting the program because there's no more inventory, even though we can't get the selling thread back. So that's kind of the model, right? So, and we want to use the joinable test just to be clean about our particular way we're writing the code. So take a look. The comments hopefully in this will help you. I'm going to open up one here on my screen as well to help narrate what's going on here. So try it out, see if you can kind of make sense of it. I'll give you guys a few minutes and then we'll talk through it a little bit. It is, like I said, it's a little bit contrived. I was trying to come up with an example that demonstrates this for you. Okay, so I'll give you about 3 minutes on that one. And ask me questions if you get stuck. So I guess I can point out that the sell worker function and the report worker function are complete. You need to do nothing with them, but you might want to just look at them and see what they're doing. Should be a very familiar model to you. Sell is just going to have an infinite loop. It's going to grab the mutex. The mutex is relating to the inventory, right? In this case, our mutex is global, so we didn't pass it into the sell function. We're just sort of using it as a global variable. And then if we got more inventory than 0, then we'll decrement it by 1. Otherwise, we're gonna break out of the loop, and then we'll unlock and be done. Right? Selling thread will quit also when it's out of inventory. Okay. And the report thread is pretty similar there too. And if you get kind of the basic thing done that's called for, you can try, detaching the reporting thread and see what happens there. I'm going to temporarily switch you over to my REPL.
Wait, why do we use joinable at all? I mean, I guess I know we use joinable, but like we're not No, we are detaching S. Well,
I mean,
oh, so join without using joinable is like a forced join, right?
right, right. If you, right, I mean, and you will crash. Like if you detach, you could try this. You could detach it and then just try to straight join it without testing it as joinable. I think you'll get a hang or
Yeah, it crashed.
yeah.
Yeah,
So yeah, once it's detached, you can't just say, "Hey, I want to join you." You have to check the condition before you can join, basically. Sorry, I
yeah.
think I lost my sharing. Give me just a second here. Trying to decide which window is the best one to go back to. Upload thread. I think this is it. So start that. Turn that off. Let's see if this will. Oops. Huh. Please try again later. What? That's so good. Okay, so I just put that up for the moment for you guys. Give me a second while I just check to see what we have coming up here. Okay, yeah, right. Okay, that's fine. All right, so I think I'll switch back to this. Just check and see what else I got coming up here. Yeah, okay. PowerPoint, sure. Okay, you should be seeing the PowerPoint screen again. Okay, let's take a look at the code. It's not a lot of code, like I said, it's just in main there. So, and this is really just to give you a model to play with, but I create this selling thread, create the reporting thread, then I detach the selling thread, right? So it's just off running, right? And I say if S is joinable, which we kind of know, or sorry, we know that it's not joinable. So it's not going to join, right? It's going to immediately fail because that if test fails. We know we can't rejoin a detached thread. So it's going to fall right through and say if R is joinable, if the report thread is joinable, then definitely wait here to join, right? And that's where we block. We block on that join right there because the thread, the reporting thread is just going to keep going as long as the selling thread hasn't depleted all the inventory. And so, I mean, this could be any other kind of, situation that we're, blocking on here. But I just wanted to characterize the behavior of both of these detached and attached threads in the same program. So you can kind of see how they work. Okay. So hopefully not totally pointless, but it gives you a working example you can come back to see how this detached and join works. Okay. Any other questions on that? Okay, cool. All right, so no, so I'm not there. It wasn't full screen mode. Okay, so there's just some of those observations. If you want to come back and read that at a later time. All right, let's look at multiple locks. So this is just one other main issue I wanted to make sure we talked about because it can really bite you. We simplified it. Like a lot of times you might have multiple locks because you're changing multiple things. You may find out that in this case, I've got mutex A, mutex B, that are associated with some specific piece of data that I want to modify. And let's say that I have, and then I unlock them because that's the right thing to do. And then in some other thread, it's not the same worker function, let's say, but it's using, let's say, the same data. It's trying to access the same data. Maybe one's writing and one's reading, right? But thread 2 here locks these things out of order. So if that happens, right, we lock mutex B and then we try to lock mutex A, this is going to create a deadlock every time. And it's not immediately obvious why, which is why it's so hard to debug these kinds of problems. But basically, if you think about it, when we grab the mutex A, we're going to wait there, right, until A is available, right? So thread 1, let's say, is waiting for A to become available. Meanwhile, thread 2 comes right along at the same time and tries to get B, right? And let's say it's waiting for B to be available, and maybe it's not available, right? So the two threads are essentially waiting on each other, right? And we can't continue, right? And if one acquires the thread, the mutex rather first, it's still going to end up in that deadlock situation, right? So we're always going to be locking unless we lock in the same order across all threads. So whenever you're working with multiple mutexes, and especially if you're, I mean, obviously if you only have one worker function, it's not an issue, but if you have multiple different worker functions using these same mutexes, you have to lock them in the same order. Otherwise you're going to end up in a deadlock situation, okay? So that's the key takeaway there. So I think we're just going to have you go in and try this very briefly. It's obviously very straightforward exercise, but you just run it and observe the deadlock, right? You're just not going to see this thing exit. And then go ahead and check the order in the worker functions that you find there and get them in the right order and run and just make sure that it executes properly. This should be pretty quick. So give that a try. I'm just going to give you like 2 quick minutes on that. And we should start winding down the lecture for the day after this one. Okay, well, let's take a look at this one. It's pretty much what it was. Nothing really that needs to be gone over in terms of the code, but just something to remember if you ever are working with multiple locks, because it'll definitely crop up. And it's not obvious at all if you don't know about this sort of thing. I'm going to touch on one more thing here briefly, just to get a few key points. I think this is more to give you vectors to do research if anybody's really fascinated in this. We're not going to have any testing on this, but bear with me for just a minute or two while we touch on this, and then I'll let you guys go. So we looked at scoped locks the other day. I think we talked about that briefly. But unique lock is a different kind of scoped locking, but it kind of defers the lock. The scope lock we saw when a scope goes out of, when a lock goes out of scope, it unlocks and cleans everything up. Deferred locking allows us to do that, but to not lock the mutex right away. And it works well with conditional variables, which is another kind of a C++ 2011 enhancement. Here's an example. Like here's a lock guard that we might get on a particular mutex, right? So we did this the other day. We have a mutex and we wrap it in a lock guard here. And when that goes away, then it's going to unlock. But here what we can do is we can create what's called a unique lock, which is not locked yet until we ask for the lock. Or sorry, it's locked, and then we can forcibly unlock it even though we're not going out of scope, right? So my guard 2, we can say unlock here to allow it to unlock, right? So this is something that we can use with these condition variables if we want. And if they both go out of scope, then they're both going to get unlocked anyway. But this allows us a little bit of more flexibility with the unique lock on guard 2 that lets us unlock that. Sorry for the extra piece of code in there. That's just a redundant.
So a unique lock is like a lock guard, but you can unlock it whenever you want.
Yes, exactly. It's sort of supposed to be kind of the best of both worlds with the versus just using the straight mutex. Because sometimes with a lock guard, you don't want to have to create local scope just to get it to go away, right? You just want to forcibly unlock it at that very moment. So the unique lock will kind of let you do that. That's kind of, just FYI. Actually, I don't know if there were any other questions on that. I don't think we're going to do an exercise on this. I just kind of wanted to put it out there real quick. And then condition variables. This is where things can get interesting. And this is similar to promises I was talking about before, but I don't think we're going to have time in this course to get into it. But in case you're interested in threads and you want to look this stuff up, these two things go together, sort of the unique lock and conditions. It allows essentially to send messages between or to threads to enable or disable certain behaviors, which is pretty cool. So we can basically lock and unlock by sending a message to the unique lock, right? And these end up being signals or synchronization primitives to kick off maybe a bunch of threads that have to start at exactly the same moment, okay? So we might notify a number of threads to wake up all at the same time. And they may then, within their worker functions, check various mutexes to decide whether it's okay to go ahead. So we might start if you think of it as a race, two threads we want to race to try to complete some task, and we want to kick them off at exactly the same time, right? We can create a lock that we send a message to where everybody gets notified at the same time, rather than in the sequence of order that I'm executing inside of my code. So as we've saw before, sometimes we create a thread 1, and we create a thread 2, and we create a thread 3. And thread 1 ends up just dominating, right? Because it got created first, and it's going to grab the locks, and it's off and running, right? So this is just a way to actually get around that problem. This condition or message sending is a way to get around that problem, so we can actually kick off all threads at exactly the same time. So here's a little look at how some of that code. So the library is called condition variable. We of course have our mutex. We create a mutex. We create a condition variable, right? And then we create our unique lock around the mutex, and I just call that LCK, okay? And then I could say condition variable notify 1, which would be notifying any one of the particular threads, right? Or notifying all of the threads. This is how we would go about doing that, right? So this code will pretty much demonstrate how this actually works. We're not going to go through this exercise today because we are definitely at our finish time, but I'm just going to leave this link for anybody that wants to look at it and for reference if you're interested in this. And if by some miracle we get a little time to come back to this and maybe look at promises to fill in some space toward the end of the semester, we will. But I just wanted to put this out there for you so you have some working code to look at, okay? Any questions before I let you go? I know I kept you longer again than I said I was gonna. Okay. All right. Well, very good then. Thanks everybody for sticking with it. And just minor words of encouragement. Hang in there. Only a couple more weeks. Everybody seems to be doing pretty good. Just kind of let me know if you have any questions. I'm always here. Thank you.
Thanks, Professor.
Have a good night, everybody.
Too.
Quick question.
Yes.
Earlier, you were talking slightly about privileges on OSs. I was curious what would happen if you tried to, for example, write a file into an area where you don't have the privilege to.
Oh, well, I mean, definitely the file system will try to stop you from doing that, right? I mean, in whatever, depending on the operating system you're working, but let's say it's just Linux or something like that, you're going to already be restricted in terms of where you can write things.
Mm-hmm.
And so if you don't have permissions for that area, then, you would be, you're basically your request would be denied. Kind of, you'd find out about it through the file open.
The user?
Sorry, go ahead.
Would it try and prompt the user?
No, not if so.
Programs run in what's it called? The program files x86 folder on Windows, for example.
Right. Yeah, if you try to open a file for write, I mean, this is probably fully separate from threads. But if you tried to open a file for write, you're going to get a failure on that if you try to open it in a location where you don't have write permissions, where that particular process doesn't have write permissions. So, and your permissions on that process derive from the fact that you launched that process. But let's say you're logged in as admin and you have total authority over the file system. Then you can unfortunately write over maybe almost any file. So it really depends on what you're on a multi-tenant system like a Linux or Unix or something like that. It depends, or even Windows, it depends on who you are when you execute the program initially.
Okay, that makes sense.
Yeah. Now, in a cloud-based situation, like Amazon Cloud Services, you're reading and writing to databases, and so those authorities to whether a particular process can read or write to a specific database is even more convoluted. You have to secure, very explicitly secure authority for a specific process and the user running that process to access a particular database. So it really, really depends on the operating system.
All right, thank you.
You're welcome. You're welcome. Have a good night.
You too.
Hi, Professor.
Hey, is that Vaughn?
Yeah.
Okay, yeah, I think it's just you and me, actually. I think Chris might have gone. Yeah, Chris just signed off. Okay, so oh, and let me turn off the. Hold on one second.
Uh,